In this unit, we'll be looking at how we can apply the derivative of a function to a variety of scenarios. The first being analyzing the behavior of a function. So we start by looking at increasing and decreasing functions, the topic of 3.1. So recall that for a function to be increasing, it signifies that over the interval that we're interested in, if a function is increasing, that means for all x1 and x2 in an interval such that x2 is greater than x1, f of x2 is greater than f of x1. That's a lot of fancy talk for basically saying that as x increases over an interval, so too does f of x, okay? As we can see right here, as we go from x1 to x2, we see that f of x1, we see that all points are greater than f of x1 as we reach x2, going up to f of x2. So we can see that our function is strictly increasing and become greater. So in terms of condition in calculus, if we look at the slope of the tangent line when a function is increasing, we see that the slope is positive. So what that tells us is that in order for a function to be increasing at a point x equals a, its derivative of the point must be greater than 0. So f prime of a must be greater than 0. Likewise, if we look at a decreasing function, decreasing has a similar definition for all x1 and x2 in an interval. With x2 greater than x1, it means that f of x2 is less than f of x1. And what that means is that we move from x1 to x2. That means our function f is strictly going to decrease in value from one number to a specific lower number throughout the whole entire interval. So if we look at what a function, what is required for a function to be decreasing in terms of calculus, we see that the slope of the tangent line of a curve when our function is decreasing is negative. So in order for a function to be decreasing at a point x equals a, its derivative point must be less than 0. Here's a summary of our conditions right here that you can jot down to save yourself some time. Increasing, f prime of a, our first derivative will be greater than 0 at a point, and then decreasing at x equals a signifies that our derivative at that specific point is less than 0. So that brings us to critical points and relative/local extrema. Okay? So we start off with a definition. X equals a is known as a critical point if the first derivative is equal to 0 or the first derivative does not exist. So we see right here where we have this cusp and corner, we see that our derivative is undefined, or we have the slope of the tangent line is 0 at these points right here, which gives us a critical point. Okay? So a critical point can either be defined as a relative/local maximum, a relative/local minimum, or neither of the two. If you do not recall what a relative/local maximum or minima is from prior classes, it's essentially a point where a graph changes from decreasing to increasing for a local minimum and increasing to decreasing for a local maximum. So there can be multiple local maxima and local extrema for a function over an interval. In terms of a more layman's term, a local minimum is just a valley, and a local maximum is just a hill. So, as we've talked about, a local maximum will occur when our function changes from increasing to decreasing. So the condition for a local maximum is that f prime of a equals 0 or does not exist, since we'll have a horizontal tangent line, or we'll have a cusp like we have right here, and the sign of the derivative changes from positive to negative, as that means that we're changing from an increasing to a decreasing function at that point. As we can see right here, we see that our derivative is positive right here, and then it's 0 at the local maximum, and then we come down here and now it's negative. So it goes positive to 0 to negative at a specific local maximum. Now on the flip side, a local minimum at x equals a signifies that either f prime of a equals 0 or does not exist, so we have a critical point there, and the sign of derivative changes from negative, like we see happening right here, and then changes to positive. This right here says f prime of x is greater than 0. It should actually say less than 0, so that's a typo on the illustration. But we can see right here our slope is negative, and then it becomes 0 at the local minimum, and then it becomes positive afterwards. So we have to look for a change from negative to positive at the point x equals a, and make sure that our derivative is equal to 0 at x equals a. All this might sound a little bit esoteric, but we'll formalize this with a practice problem here to see in a second how we do this. So in terms of analyzing a function's behavior, to analyze increasing/decreasing intervals and locations of local extrema, we can make use of what's called the first derivative test. The idea is that we first determine the derivative of our function f. The second step that we're going to do is we're going to set f prime of x equals 0 to solve for the critical points, or we also look for x values where a derivative does not exist. This occurs, as we've seen, mostly with the quotient rule when we have a function in the denominator, or an x value in the denominator. So what we're going to do then is in between each critical point, we'll evaluate the derivative to determine the sign of the derivative over the interval between critical points. And then lastly, we'll interpret our results. So if I find a critical point, let's say, if I find two critical points and then I use x equals a as a test value in between those critical points, and I get that derivative is less than 0, then that tells me in between the critical points, f is decreasing over that interval. So let's see what this looks like in practice. For the function f of x equals 2x cubed minus 6x squared plus 3, we first want to determine the intervals where f is increasing, 2 determine where f is decreasing, and 3 classify the critical points of f. This is a pretty standard free response type question that they throw in the exam, especially as pertains to function analysis. So we can actually cover all 3 of these with the first derivative test in just the 4 steps outlined on the prior slide. So first step is we take the derivative. So the derivative of 2x cubed minus 6x squared plus 3 is going to be 6x squared minus 12x. The second step is that we set our derivative equal to 0 now, and we solve for the zeros. We don't have anything that's going to give us a does not exist here, since it's a polynomial, so we're just strictly going to look for zeros as polynomial. So 6x squared minus 12x, we factor it, we solve the critical points, we get that the critical points are x equals 0 and x equals 2. So now what we can do is we can set up a number line to represent what's happening with our function, with our derivative. So we know at 0 and 2 we're going to have critical points, and then we can use test points in between 0 and 2, or beyond 2, or less than 0 to see what the sign of our derivative is. So for less than 0 I can use x equals negative 1, which gives me a number for my first derivative that's greater than 0. For x equals 1 between 0 and 2 we're going to get something less than 0. And then for x equals 3, which is beyond 2, we're going to get something greater than 0 again. Again, you can use any test point between the critical points in order to determine your function's behavior. So we see a derivative is positive for less than 0, negative for between 0 and 2, and positive for 0 and 2. So that tells us that our function's increasing from negative infinity to 0. We have a local extrema, or a local maximum, at x equals 0, since our derivative is going from positive to negative. And then from 0 to 2 we have a decreasing interval. And then at 2 we have a local x equals 2 we have a local maximum, because our function is changing from because our first derivative is changing from negative to positive. And then lastly we can see for greater than 2 our function is going to be increasing because the derivative is greater than 0. And again, this is just an interpretation of what I just said on the last slide. They do ask you to explain on the FRQ section, so something like this suffices perfectly. F is increasing over negative infinity to 0 and 2 to positive infinity as f prime of x is greater than 0 over these intervals. Something like that, a nice short statement. You don't have to write a whole diatribe, and that summarizes your results. And then we would apply that to everything else. So f is decreasing over 0, 2 because the first derivative is less than 0 over this interval. So we can also use this to analyze the graph of a first derivative. Okay. So the key to analyzing graph of a first derivative is you're not looking at the function f here, but you're looking at the function or the graph of its derivative f prime. So the values of f prime are associated with the y-axis. So the derivative is positive over this region right here, 5/4 to 2, and then 2 to positive infinity, because f prime is above the y-axis, or above the x-axis, and it has strictly positive values right here. Likewise, for x less than 5/4, the first derivative is negative because we see that the first derivative curve is in the negative part of the y-axis down here. So we can use this to determine critical points and local extrema and increasing and decreasing intervals. So first we recognize is that the derivative is 0 at x equals 5/4, and 2 since we have a y-intercept for the curve of our derivative here. The derivative is positive over the open intervals 5/4 to 2 and 2 to positive infinity, as we can see right here, because it's in the positive region of the y-axis. The derivative is negative over the open interval, negative infinity 5/4, because we see that for any number less or any x value less than 5/4, our derivative is in the negative part of the y-axis. So we can summarize these results in a table such as this, and these tables are also something they'll give you on a free response. They're quite common in terms of interpreting behavior. So we can say x value is right here, and then the value of the derivative right here. So for negative infinity to 5/4, we're negative. The derivative is negative. For x 5/4, x equals 5/4, the derivative is equal to 0. For between 5/4 and 2, the derivative is positive. For x equals 2, the derivative is 0. And then for any number greater, or any x value greater than 2, we're positive. So what we can do now is we can interpret these results. So this is a graphical example of applying the first derivative test to a graph. So now we can interpret our results here and say that for negative infinity to 5/4, f is decreasing because the first derivative is negative over this interval. For 5/4 to 2 and 2 positive infinity, f is increasing as f prime of x is greater than 0 over this interval. The first derivative is greater than 0 over this interval. And then lastly, at x equals 5/4, there is a local minimum as we have a critical point here. Again, we see that the first derivative is a y-intercept at this point, so it equals 0, and the first derivative changes from negative to positive, telling us we have a local minimum at this point. At x equals 0, we have neither a local maximum nor a local minimum because even though we do have a critical point, we have no sign change going on here. Our derivative is positive, then it reaches 0, and then stays positive. So we have neither a local maximum nor a local minimum at this point. And that just summarizes what I said in the last bullet point right there. Technically, what we'd call this is a saddle point when it's neither a local maximum or local minimum. But most of the time, the exam will just ask you if it's local maximum, local minimum, or neither. And this is our video for function analysis using the first derivative.